Greetings and welcome to Physical Science in the AM. In case you've just joined us, this is Physical Science in the AM, already in progress. We're looking at objects that are placed on the focal point, and we have no image. It's the flipping point, where you go from virtual to real, erect to inverted. Nothing, and we're just showing that. Rays from the template we use that. Okay, it goes through the focal point is the one rule, right? Now, if I try to use the second rule is, and I'll do it in disappearing end, that rays from the focal point are going through the focal point. That doesn't work. So don't. I'm doing this. Just don't do it. It doesn't even apply here, right? Because how can you? Yeah, it's wonderful. That rule wouldn't apply. But if I try that center rule, get some geometry on it. So I'm going to just line this up. And what do you notice about these? I line them up. They're parallel. Okay, I'm going to draw in some arrows. So this hits the mirror and then goes through the center and bounces back. These are parallel rays. This is why you get nothing. Parallel rays never meet up, right? And so I'm going to write down here. Parallel rays never meet. That's why there's no end from our geometry. Okay. Yeah, that's number 5. Object between F and P. We know this. This is the close-up. This is where you're larger. I'm going to just say this. Because I think we know this. It's larger. So we're going to drop it too. Orientation. You say erect in this. And that means it's virtual. How can we predict where our virtual image is? Another object there. We'll use these rules. I'll tell you which rule. Actually, I'm going to just use a dotted line. Now, I'll do the full rule and then we'll see. Why I'm doing it. I always draw my, like I lay my ruler down and I draw this. The dotted line is always behind the mirror because it's not actually going through the mirror. What is happening is that center rule, I like to use that first, is that rays come in, bounce off the mirror, and then head back. Right? Okay. But I'm telling you because it's virtual. A virtual image means it's actually appearing behind the mirror. Rays of light don't actually converge. That's why you can't put it on this. And we're familiar with dotted lines behind the mirror from flat, plane. Then we choose another rule. I tend to like the first rule, as in the one that says rays that go parallel to the principal axis hit the mirror and then go through the focal point. I'm going to use a dotted line to line up the next one, and then I'll make it. So really, that dotted line is only there to guide me with this. The actual rays of light bounce through the focal point. That's the solid. So, parallel hits the mirror, goes through the focal point. Right? That's what you're drawing solid. But extend that. where the virtual image appears to your eye. So then I'm going to draw. Here's where they converge, the virtual ray. This is your virtual image. And it definitely is large. Geometry tells you that it's always large. Question? Check. Okay. So this is what we've seen. Object at a distance. Now this one is hard to do. But you have something really far away. So the sun is super far away. It's so far away that light rays coming from the sun. I'll do something first. If this is the sun, yes, we have light rays going in all directions, right? But the ones hitting Earth, Earth is here, they're all basically parallel rays. Right? So that's at an extreme. You don't have to even do that. But the idea is that if something's at a large distance, the rays of light coming from that point or that object are coming in parallel. Okay? If they come in parallel, we already have done this down here, but we're going to get it down here. Okay? Grab some rays. Oh, on. Back to this. Okay, now any rays that come in parallel. What's the rule on a converging mirror? Parallel rays focus. The thing is, they all do. So I'll do it again. I'll just pretend it's 2 rays and that's it. We've done it with 5 rays, I think. Or was it 3 rays? On the first page of this. All the rays come to a point, the focal point. You don't get an image, really. You get a dot of light. It's truly far away. Now, this is where you can intensify the sun's rays and start a fire, not just with a lens, but with a good curved mirror. This is the spot where a satellite dish has its receiver. Right? Okay. These don't have to necessarily come in at straight on the principal axis. I don't know if you remember, I forget who was holding, was it Keegan, who was holding, or actually I think it was Mariah, I forget. Who was at the board with, who was Rory? That's right, okay. When Rory was there, we were holding the mirror and the ray box at the same time, and it wasn't even straight on, and it would come in at an angle. The focal point, you'll get a focal point that kind of moves at the same distance, but it doesn't have to be straight on. So don't just all the rays converge to a point. So you don't want to get in. Okay. Yeah. We wrap that up. You guys have some. Yeah. I have these questions, and I'm going to ask you to try these, but I want to also go over the assignment a little bit. The people that Sheldon and others. If you want a chance to get them back, I'm going to talk to you quickly about these questions. But these questions, look locate the center and the focal point in each diagram. This time, I've given you the object and image. So you just use the rules, knowing that I'm going to do a rough diagram here, but if this came in and it goes, yeah, okay, that's probably the focal point, right? And then what about that center rule? Well, that would be this one coming in and then going back on itself. That'd be where the center, like, you guys follow me? You go backwards on some of the rules. Okay? This is behind the mirror, so this is obviously a virtual. Well, okay. You just look back if you want. But I get the object of this set of questions. Without the center focal point, you have the object in it. Fine. I will give you time to do those as well as I am probably doing now. Or help with that.